Okay, it's great pleasure to have Levin Maier from Heidelberg. The title is really long, but here's the title here, and take it away, Levin.
Okay, great. Thanks for the introduction and also for the opportunity to present my research here. So I will talk today about Manis critical value for the two-component Hunter-Saxton system. Where Manis critical value, that's a tool to study finite dimensional Hamiltonian systems on typically on compact manifolds. And on the other hand, the two-component Hunter-Saxton system, it's a nonlinear PDE. The aim of that talk is to bring that two different worlds together. So the plan of the talk, first of all, I try to give you a background on geometric hydrodynamics to recall basic notions. Then we will go to the toy model, magnetic geodesics on S3. Then we will go to the most possible generalization of that toy model, the magnetic to Hunter-Saxton equation as a magnetic geodesic equation. So where we have like a PDE on on a finite dimensional space, or magnetic geodesic equation on a infinite dimensional space. Then we will see what it means to have like a Manis critical value for that type of PDE. And then in the end, we will go to the key lemma to bring the toy model and the PDE together. Like the key lemma is the dynamical reduction of everything to S3. So we will start with the background. So in his most cited paper, Arnold sketched the following thing, or proved. So we start with a closed Riemannian manifold, then solutions to the Euler equation, which has this expression on a finite dimensional manifolds are one-to-one, then solutions to the geodesic equation on the group of volume preserving diffeomorphism equipped with the L2 metric. So the philosophy is either to have like a really hard equation, like a PDE, or a nonlinear PDE from fluid dynamics on a nice space or closed Riemannian manifold, or having a nice equation like a geodesic equation on a not so nice space, so the group of volume preserving diffeomorphism. But since I'm a geometer, I prefer to have the geometric equation and then tackle the problems. Then another directions is either you can change now the group or the metric. That was also done in the past, like by Boris Kezin, Jared Mirolik, and Jonathan Landons, more or less independently. They proved that the solutions of the Hunter-Saxton equation, which has the following expression, are one-to-one then to solutions of the geodesic equation with respect to the H1 metric on the group of all diffeomorphisms on S1, which are fixing one point. So in terms of mechanics, what's then in Hamiltonian dynamics the next step, going from geodesic equation to Newton's equation, so having a potential force. And that's a part of the next slide. So Newton's equation, it's written, has this expression, and there is a nice survey paper from Boris Kezin, Jared Mirolik, and Glazimodin, which surveys all of Newton's equations which can be written, which are corresponding to some PDEs. So there's a whole zoo of PDEs which can be written as Newton's equation on an infinite dimensional space. Like some of them, for example, Invisitz-Burger's equation or optimal information transport on the diffeomorphism group, or Hamilton-Jacobi or Schrödinger equation on the space of densities. So, but the next step here, the next natural step is now to ask, what about charged particles? So can one rewrite also some PDEs as magnetic geodesic equations? And coming to that, we will introduce now the setting, what it's mean to be magnetic geodesic equation. So first we start with a Riemannian manifold Mg and a closed two form sigma. Then we have like Y is a bundle endomorphism of the tangent bundle, uniquely defined through the following expression, since the Riemannian metric is non-degenerate. That defines us a unique bundle endomorphism. Then we call a curve gamma a magnetic geodesic of strength S, if and only if gamma is the solution of the following ODE, where I like to think about the ODE as a linear deformation of the geodesic equation in the velocity, because Y is linear in the velocity, so it's kind of a linear deformation in the velocity. Also note, if you choose here S equal to 0, you recover the geodesic equation. So it's a natural generalization of the geodesic equation. So if then we will go to first example, to the example in S3. So we look at S3 as the embedded submanifold in C2, where we equip C2 with its standard Hermitian product. Then we get the round metric on the free sphere if we restrict the real part of the Hermitian product to the tangent bundle of the sphere. That's how you get the round metric. Then recall also, you're all familiar, I guess, with that, but you can also express the standard contact form on the free sphere by restricting the imaginary part evaluated at one point Z to the tangent bundle of S3. And also then you see the derivative of the contact form, standard contact form, is given by the restriction of the imaginary part of the Hermitian product on C2 to the tangent bundle. And this will be our magnetic field, so the sigma before, and this will be our metric. Then also the psi is here the standard contact structure. Then we can define a projection of the tangent space of S3 to the standard contact structure. And the standard contact structure is also closed by multiplication by complex multiplication with I. And then if we use this as magnetic field and this is metric, this will be I times pi xi. So this will be our Lorentz force. The magnetic geodesic equation reads as has the following expression. So we have here the geodesic part and then S times I times the projection of the velocity to the contact distribution. And then if you do some calculations, it follows that each magnetic geodesic is given by P1 times e to the theta 1 plus P2 to the e to the theta 2 t, where P1 and P2 are complex orthogonal. So that's joint work with my advisor Peter Albers, Gabriele Benedetti, and myself, and we will publish it soon in the next 2 months. And the point is here, since P1 and P2 are complex orthogonal, they are spiraling on torus. They're staying on tori, so they're spiraling there around. And that's also part of the next picture. So we have here the magnetic system, S3, equipped with the round metric and the standard contact form as a magnetic field. Then if we chop up S3 into 2 solid tori, that's the first tori and that's the second one. Here you see the Rabe orbit if we set the second complex coordinate to 0. Here's another Rabe orbit if you set the first complex coordinate to 0. Then as I mentioned before, magnetic geodesics, they're staying on tori, so they're spiraling around. So here you see the magnetic geodesic, it's spiraling around the Rabe orbit. And the first integral, the angle between the starting velocity and the Rabe direction is also an integral of motion, where it's cosine, that guy here's an integral of motion. But often one would, at the beginning, we expected that magnetic geodesics on S3, they always close up. But that's wrong, because since they're going on tori, they don't have to close up. Then the next part is, now we compare magnetic geodesic on S3 with magnetic geodesics on S2, and we use the Hopf projection. So we go from S3 to S2. Then all magnetic geodesics, so if they project them down, they're downstairs closed, but one would expect at the beginning that they have all, if I have magnetic geodesics upstairs on S3 with a fixed magnetic strength and velocity, that the radius downstairs is fixed, but that's not true. So computation shows that the radius downstairs, so the projection here, it's dependent on the magnetic strength and the angle to the Rabe vector field, so it's varying. That was kind of surprising to us. Then we will go to the next slide. The first remark to this is, as I said before, the magnetic flow on S3 is not Sol, because they're not all closing up. Then the second thing, which I was proving together with Johanna Bimmermann, which is the part of the paper, the magnetic flow on S3 is integrable. So it has 3 independent integrals of motion, so it's quite nice. Then, joined with Peter Albers, Gabriele Benedetti, and myself, we have proven for all P, Q, and S3 there exists a unit speed magnetic geodesic of strength S connecting P and Q and S3 if and only if S is between 0 and 2. Second part is for all S bigger or equal to 2, there exists no unit speed magnetic geodesic of strength S connecting 1, 0 and 0, 1, so the yellow and the purple orbit on S3 with a unit speed magnetic geodesic. Then note C equal to 2 is exactly Manet's critical value, so we computed it in that setting, and it's exactly Manet's critical value, so you see the dynamics change drastically and Manet's critical value. And then the second remark is this direction would also follow from a way more general theorem from Contreras, but that theorem is limited to compact Riemannian manifold, and since I want to generalize it to infinite dimensional manifolds, we will have done here independent proof. So then we will do to time two constraints a big jump to the most general possible generalization of the system. And we will go to magnetic geodesics on infinite dimensional space. So G is in this setting, infinite dimensional Lie group. It's the semi-direct product of all diffeomorphisms of S1, semi-direct product with maps from S1 to S1, where the 4 pi is more to normalization, so it's not so important. And the Sobolev class, we also don't care. It's only for completeness here. Then we have proved, then if phi tau is a magnetic geodesic in this group equipped with some metric and a Lorentz force of strength S, if and only if U, which is defined as the time derivative of the flow phi, pulled back with phi inverse and rho equal to tau t. So the time derivative tau pulled back with phi inverse is a solution of the following nonlinear PDE, which I call magnetic two-component Hunter-Saxton system. And the name, and note first, the magnetic Hunter-Saxton system is a linear deformation of the two-component Hunter-Saxton system, which is underlined in red. And why it's a linear deformation? Because the two-component Hunter-Saxton system, this is exactly a geodesic, solutions to that corresponds to geodesics in the Lie group Gn. And as I said before, I like to think about magnetic geodesics as linear deformations of geodesics, so in terms of the equation. So one would expect also that the PDE is a linear deformation of the corresponding PDE. And then the next remark, so that is the geodesic, this was proven before by Lennels. Then the next remark is the magnetic Hunter-Saxton system has as the two-component Hunter-Saxton also blowups, but I used later on geometry to get explicit criteria when the PDE has blowups. And to continue here, then also one can go as always with PDEs to completion, or I constructed here completion of the space, like we have MA0 is C, which is the natural completion here, where M0 is C. Is the space of absolute continuous function from 0, 1 to 0, 1, 0, 1, 0, 1, where f is non-decreasing, fixes the endpoints. Then the first remark is the weak magnetic flow on that space exists globally. So we have a global flow on that infinite dimensional space. Second one is we used the correspondence developed before, that if we have a weak magnetic geodesic in that space, then the corresponding solutions to the PDE are global weak solutions. Since we have a global flow, a global weak magnetic flow, we have also global weak solutions. Only short, the first remark is for S equal to 0. This was already proven by Markus Wunsch in 2011. And the second remark here is we can really use here geometric arguments to prove that they're global weak solutions. That's quite nice. Then we will have that in mind, and we'll go now to Massenet's critical value for the two-component Hunter-Saxton system. First, the first part of the theorem is if S is less than 2, there exists for all GH in M0Z a weak unit speed magnetic geodesic phi tau connecting of strength S in M0Z connecting the identity 0 and GH. That corresponds in the picture before to you can connect the yellow orbit in all points in S3 with a magnetic geodesic if the magnetic field is not so strong, so less than 2. And then if S is bigger or equal to 2, there exists no unit speed magnetic geodesic phi tau strength S in M0Z connecting the identity 0 and identity 2 times identity. And that's exactly corresponds in the picture to before. We can't connect points on the yellow orbit and the purple orbit before. So then remark to this, C equal to 0 is Z to equal to 2 is exactly Mané's critical value for that PDE. So that there you can also define some notion of Mané's critical value. Then, and it's also the first time, I guess, in literature that someone defines something like a Mané's critical value for a PDE. Now we'll move on and bring in the key lemma, both worlds together. So that's kind of the key lemma. We have here NM0Z or G, there lives the weak magnetic flow or the magnetic flow. Then there's a dynamics preserving map from that M0Z to an open subset U in an infinite dimensional sphere, where we could equip that subset with a round metric and a standard contact form or a contact type form in infinite dimensions. And here that sits in the L2 sphere. And it turns out that one can reduce the dynamics here to a totally geodesically embedded sphere, free sphere, which is flow invariant by the magnetic flow. So we reduce the magnetic flow here in that space to the dynamics on S3, so which we investigated in the beginning properly. And then it turns also out the magnetic flow here corresponds to the solutions of the PDE here. So we can use now the magnetic flow and go all that arrows back and tackle with magnetic geodesics on S3 solutions to the PDE. And this is like a contact type form. So that's the key lemma. That was quite surprising, but it's also quite nice. And last but not least, I wanted to mention some further directions. The first one is like, together with Johanna Bimmermann, I uploaded a paper some weeks ago on the Hofer-Zehnder capacity of distangent bundles of length spaces, and we computed that they're independent of the prime P. And the main method here is we used like magnetic billiards induced by the magnetic flow on S3. So that's one big part there. So really computationally, it's similar. That's why I mentioned it. Then another, and we in particular proved that it's not equal to the chromorph width of the space. Then the second generalization, it's quite natural. We had like a PDE now on S1. So what one could ask, what happens, can one define something like the magnetic two-component Hunter-Saxton system also for closed Riemannian manifolds? Or what is there the notion? Then what's also, since the magnetic flow on S3 is integrable, one should also expect, or one expect that also the corresponding PDE is also integrable. So processes infinitely many, that's work in progress, and also that it's well posedness, so that's work in progress. Another thing one could also ask is, as always, like conjugate points of the flow. That's also work in progress to see if the magnetic flow on the infinite dimensional Lie has conjugate points or not, and what that means for the PDE. Another thing would be also like to prove there are some magnetic cutoff examples. So one hope would be also to have now magnetic cutoff examples for corresponding PDEs and finding there the nice equivalence. And the dream would be like to prove something, to have defined infinite dimensional capacities in some meaningful way, or adapt already existing definitions of that to prove a non-squeezing property for the Hunter-Saxton equation. And that's it. Thanks for your attention.
Thank you. Let's thank Levin for this talk. Any quick questions for Levin?
Can you, I mean, it's maybe a philosophical question, but can you say anything about magnetic flow on non-round spaces, let's say hyperbolic, for example?
Yeah.
Yeah, I think like on the Poincare, do you mean on the Poincare disk, for example? Yeah, there it's a bit different, but there you can see them, as far as I understood it, if I understood it correctly, you can see the magnetic flow as a like interpolation between the geodesic flow and the horocycle flow. So exactly in at magnetic critical value, you hit there the horocycle flow. So you deform it.
Okay, so we will continue the discussion. Let's thank Levin again for one last time.